It's a bit like a Groundhog Day. I mean, then you have that head, let's say, it's created, and then as you use it, you feed in information that goes into context. But this context is ephemeral. It's like writing something on a piece of paper and just storing it, the notebook, without ever internalizing this knowledge. There's no link between the queries, like between whatever you put in your LLM or how it's being used and how the world evolves, and its weights that were set once at training.
In this episode, I talked to Zuzanna Stamirowska, CEO and co-founder of Pathway, a company that's working on what comes next after large language models to power the next advances in AI. This is a conversation I can't wait for you to hear because it helped me understand today's AI models at a level of depth and precision that I didn't have until now. I met Zuzanna a couple months ago at a dinner in San Francisco, and I was so impressed by what her and her team were building that I asked her to come on the podcast so that you all could learn about it as well. Pathway has come up with a new technology and a new architecture for AI models that solves some of the fundamental problems that LLMs have with memory, hallucinations, safety, and costs. The Pathway team first published their paper and proof of concept in October 2025, and they are preparing to launch their first product to reimagine the future direction of AI. I also talked with Zuzanna about her background in research and game theory and how she's using the massive advances in AI to build a different kind of startup that's prepared to thrive in such a rapidly changing environment. All right, so here it is, our conversation with Zuzanna Stamirowska of Pathway. Zuzanna, for those who aren't familiar, tell us a little bit about what Pathway does and about your role at the company.
Absolutely. So at Pathway, we are building AI that autonomously and continually learns, evolves, and reasons. So our vision is to bring AI with no limits and one that can be sustainable. So if you were to look at the equation of the cost intelligence per dollar, we're working on that equation from both ends, enabling more intelligence, actually empowering, making breakthroughs on just how AI is being built, and at the same time making it more efficient, such that the physical limits of the earth can actually handle it. And for my role, I actually started it. So I'm a co-founder together with Adrian Kosowski and Jan Horowski. We started Pathway, and I'm the CEO, so I'm extremely lucky and privileged to lead a team of incredible researchers. I'm a researcher myself, and it's a bit how we got together. And pretty much touching, and seeing the cutting edge every day.
Yeah, well, I've been very impressed by what you're doing. We got the chance to meet in San Francisco at a dinner.
This was very good pasta, wasn't it?
It was very good pasta. It's true. It was excellent. And the salad actually was also outstanding. No, it was really fun. And I got to meet you and Adrian, your co-founder. And that was just a bit of a revelation to me. There's a lot of people that are working on a lot of stuff that sounds very similar in AI today. And when I heard what you all were working on, thinking about kind of what's next after LLMs, that really piqued my interest, of course. And so had to have you on the podcast. For the audience, tell us a little bit about how Pathway got started, how long you've been doing this, and, what was the problem that you all really set out to solve?
Of course. So we are in NeoLab. All right, NeoLab, pretty much, I think the definition by now is that a lab that works on AI that is not OpenAI or Anthropic, first wave of the big AI labs that were fighting to scale up the transformer. And now we're doing things that are different. We made that bet in 2024. And back then, I created something that internally I called the dogma of differentiation. Because in order to actually make it worth our lives, because this is literally the size of the bet we're doing, right? To make it worth our lives, we knew we needed to make something, we need to build a moat that would be so deep that it would have a chance to stand against, ultimately, the transformer. So I think for the listeners, it may be interesting to know that the teen GPT is a transformer, the piece of, let's say, math that was announced in the paper called Attention is All You Need. And this is the math that pretty much carried us until now. All this AI revolution that we're seeing, that, I mean, I think in the public kind of consciousness started with GPT-3. It all started with the transformer and Attention is All You Need paper. And in fact, all the models that we're seeing out there are built on top of that. Yeah. So they all feel the same, they all behave the same. They're all sequence models. Most of them are language models, right? We say LLMs because they're trained on language, because language has just such beautiful sequences. And indeed, transformers were built like with a lot of language, let's say, in it, or maybe in how people were working on AI, right, around that time. However, it comes with fundamental limitations, and those limitations are highlighted even by the very authors of the transformer. So it's undisputed that transformer has limits. Like, there's pretty much no debate whether or not transformer per se can take us towards continual learning. You know, the real capability of learning over time with experience by updating the weights or updating the actual skills, but real deep kind of skills that a person would have, right? There's a fundamental problem with memory in transformers, which is kind of linked to this, the issue of continual learning. So as a user, you may experience the issue of context windows that you run out of, or the issue of state tracking. So I'm just forgetting kind of context of what mattered, right? In the past, while the LLM is like the way your model is solving a problem. It's something that people see very often in cybersecurity, for example, when they deal with large code bases. It becomes even trickier as things start to change across the system that you're kind of trying to track. So these are things that are fundamentally difficult for transformers. Then let's say until late 2024, we had the pure transformer, and then a beautiful thing happened that was 01 and then 03 with reasoning, which is a chain of thought added to the transformer. And chain of thought allowed us to work through problems somehow, right? But we're still in the realm of solving problems step by step, kind of token by token type of way, which is very limiting and also leads to an explosion of tokens. And this is something that we knew. We actually knew very early on. The moment we made this, we actually decided to work on the post-transformer architecture. We knew chain of thought would be very demanding in terms of compute. And we also had this very strong feeling that thinking shouldn't be limited to language. Reasoning shouldn't be limited to language. And then we're also somehow on this journey, being scientists, to understand why AI is working, because we felt like, okay, we've built the steam engines of thought without knowing what thought is, or, where a concept is. It's essentially about having thermodynamics. So we felt like, okay, how about first of all, we study the steam engine, okay? we see what is, let's say, folklore, what is true, what matters, what doesn't. Then we try, at least to an extent, understand the rules and find this kind of micro to macro passage of, okay, how intelligence, how reasoning emerges, hopefully from local sparse interactions. That was a strong thesis we had. And I mean, I came partly with that intuition to the team. And this allowed us also to make decisions, design decisions in our research that were very strategic. Because since we had this understanding, we were not losing this much time on side quests. And maybe for people who are not so familiar with how AI research works or worked for the past years, it is right now fundamentally an empirical science, or I would say discipline. So generally speaking, we run experiments. You see if experiment moved your loss function, for example. If it moved it, you're happy. If it didn't, then you're not happy, and you say an idea wasn't worth it. To get to the place where we managed to get to, we needed to take a number of hits. We actually had to change 5 things, and every time we're changing just a single one, or 2, or 3, we're taking a loss, we're taking a hit. It wasn't working. So without having this theoretical model of how we believed, the system should work, we wouldn't have done it. We wouldn't have that.
Okay.
Wouldn't have had that conviction, but ultimately, this is science. So
Sure.
we had a strong model, right, about what we believed would work, and this came somehow from our backgrounds, and this computation complexity. I come from complex systems, AI per se, but Jan, our CTO, actually worked with Jeff Hinton. He was the first person who applied attention to speech, which means we kind of knew what sort of side things were being done, like why Transformers won, and also Łukasz Kaiser, who is a co-author of Transformer and also one of the inventors of O1, actually reasoning. He was the first check-in pathway. So we had this very intimate knowledge of what was explored, why Transformers won, where the limits are, and we didn't need to be convinced of that. And second thing is somehow just courage.
Okay.
Because if you were to go to NeurIPS, and I remember NeurIPS when it was still called just NIPS,
Yep. NeurIPS is, for those who don't know, it's the biggest academic AI conference where all the world's leading AI researchers come together, at the end of December, in December sometime.
Yeah.
And yeah.
So if you were to go to NeurIPS and say, I think I will make a smaller model, I'll make a different architecture, for years they would just laugh at you. Actually, until October last year, people would just laugh at you if you were to say something like that. Somehow, especially in the West, I'd say there was more innovation coming from the East. It's an interesting paper from China. Actually, we saw developments with DeepSeek that shown to the world. That was the most interesting thing for me in the DeepSeek moment, was that they've shown that you can actually mess up with training. You can do something in architectures. So this was fun, but it was sociological in a way. And of course, then this goes along with investors. You need to find investors who are, who have this first principles type of thinking, see the market kind of far ahead and place their bets. I mean, we're very lucky to get the cap table that's just extremely, extremely supportive. And so this is how we got on this journey. And I think I'll leave it to you to ask questions because I went on the monologue.
Yeah. No, that was good. So, when I met you, one of the things that you had explained was that today's LLMs, today's models, it's miraculous how far they've gone based on the limitations that there are, as you mentioned before, that they have kind of exceeded expectations in terms of how far the model could go. And some of these things are led to, like you mentioned, the reasoning models was a leap that sort of extended some of those possibilities. But could you talk for a minute? You mentioned the limitations, because fundamentally what you're trying to do, Pathway, what you and your team at Pathway are trying to do is trying to build the next model after LLMs that sort of exceeds the capabilities of LLMs and transcends the limitations of LLMs fundamentally. And so maybe just for those in the audience who don't understand what the limitations are, they probably are going to recognize some of them, but why don't you just sum those up for me, like the fundamental limitations of LLMs that you all are trying to supersede?
Absolutely. So we are building a post-transformer model based on the post-transformer architecture. So we're literally changing the T in GPT, if you wish. And our architecture is called BDH, Dragon Hatchling, kind of sparking a lot of cool memes with dragons around the internet. And the limitations that we have in Transformer, and this is something you all know and you all experience when, I'm talking about the audience, is that whenever you have a model, it's trained once. So you get the model and it has a serial number, right? It has a name and a serial number. Because when you train an LLM, you feed it with data and you create something that's called the weights. That's, let's say, you create the brain of the model. They're created once. It's a bit like a Groundhog Day. I mean, then you have that head, let's say, it's created, and then as you use it, you feed in information that goes into context. But this context is ephemeral. It's like writing something on a piece of paper and just storing it, the notebook, without ever internalizing this knowledge. There is no link between the queries, like between whatever you put in your LLM or how it's being used and how the world evolves, and its weights that were set once at training. And hence we need all those huge, gigantic training runs. Every time a new model release is coming. That's why we need to burn all this compute. Because you need to train them once. So this is one. They have like no way to transfer experiences, questions, the things that you feed into them from context to their weights, their kind of long-term, we call parametric memory. And they suffer from something that we call catastrophic forgetting, actually. If you try to do it, there is some sort of like an effect that makes it forget the previous things that they've learned. And this is not something that happens to humans. So if you guys have seen the movie Memento or the Groundhog Day, every morning the main kind of character wakes up without the short-term memory, without remembering what happened, and then they start leaving sticky notes or tattoos, right, to themselves to kind of know what happened. Right now, the memory that we experience in products and AI products works like those tattoos or sticky notes. And then, of course, it gets larger and it gets better because we do a lot of engineering around it, right? I mean, as AI community, there is so much engineering going into it. So we're building large databases. In fact, it's like a database. So you just store things in the database. You have agentic systems that just compress and push around pieces of context, information about your interactions with your model around. And then it gives us an impression of memory, but it's not learning in the way we learn, right? It's a bit like a student who would come to an open book exam without ever having read those books and without ever having understood what really happened there. So unless you internalize knowledge, you can't get further. You're not updating or building frameworks for reasoning that would ultimately allow you to solve new problems. And the second thing is that transformers, so there's the fundamental memory problems in LLM. It's just true. So we call it continual learning. They cannot learn continually. They cannot learn with experience. And they have trouble dealing with the notion of time. So memory kind of has to happen over time, right? So they're static. Imagine they're static, trained once. And then, yes, there's a lot of engineering. There's an entire world doing engineering around LLMs right now.
And by that you mean, Zuzanna, like the fact that you can create projects and you have sort of some static things that every time you ask a question in that project, it always accesses the same information so that it will try to give you, it sort of will imitate memory a bit.
Yeah.
Or when you can create a profile about yourself in there and you say what you are, what your job role is and background about you, and it's sort of it's overcoming some of those memory gaps by like reading those files every time that you ask a question.
Exactly.
So those are like the workarounds to this memory problem.
But the difference is between your own family doctor who knows you've known your mom, maybe knows your kids and knows your entire history, where you live and how you eat and how you party, and having somebody who sees you like a different doctor at every time, who reads your file, probably just a recap of your file, right?
Okay.
That's the difference. There's a difference between having kind of internalized knowledge versus a recap.
Okay, so that's the first one, is the memory problem. And then you were just about to say the second one.
The second one is with reasoning. Right now, the way we do chain of thought, so we're moving from like pure LLMs, we're moving to the chain of thought system. So that happened with O1, O3. And chain of thought reasoning happens in language. So thoughts have to be expressed in language, and the model has to work through the problems in language, verbalizing everything. Try to ask a chess player to verbalize his thought process, or her thought process while doing that. It just wouldn't work. That's not how thinking works. Which is something that somehow we actually learned, we discovered. We were hoping, when we started at Pathway, we were hoping that language would get us further with reasoning. But it appears that language already imposes too much structure or too many limits on reasoning itself. And especially if when you're a chess player, you kind of see a number of possibilities at the same time in your head. You know which ones are less probable. You kind of feel it, and you have a certain shortcuts. I mean, sometimes you find yourself in a new situation, but you find an analogy to something else. So over time, as you work through problems, you create some shortcuts for reasoning that you can actually use to treat situations that you haven't seen before. And transformers, as such, are terrible at games. So chess is one example, right?
Okay.
There are Atari games. There's an entire lab at NYU, in fact, that deals with games. And they are terrible at this. Because of this need to process everything sequentially and having to verbalize things.
Okay.
So what is needed is this actually freedom for the model, to think in abstract thoughts, like a chess player. And this is something that we managed to get. So we managed to get to a place where we have models thinking, us being Pathway with BDH, we have models thinking in abstract space without verbalizing everything and the chain of thought.
So what is BDH? Is BDH an acronym? What does it stand for?
It is. So this is an acronym. So our architecture was, so BDH is a post-transformer architecture. That was launched in October last year in the paper. So this way I was telling you that until October last year it was very weird, because somehow around our paper and a couple of other papers, and all of a sudden it became okay to say that, listen, we're reaching the limits. And BDH, the acronym stands for Dragon Hatchling, and the B honestly was added just as a letter for a three-letter acronym because it sounded better. But then Łukasz Kaiser says that B should stand for beautiful because of how
beautiful Dragon Hatchling. All right.
Beautiful. The math of this paper is pretty beautiful. So this is let's say the very basic architecture that we published that already gives a number of cool features. I mean, first of all, it gives native memory. So we just explained how in Transformer and LLMs there is no memory. There we get memory natively, in the learning process itself. So this is there. And then it has a number of nice implications for interpretability and safety, but I guess we'll get into this.
Ah, yes. Okay. So why Dragon Hatchling? Why did you name it Dragon Hatchling?
Do you know Terry Pratchett?
A little. My wife does. My wife reads Terry Pratchett, but
I will send you the book. I will send you the book, or at least the part, where it all happens. So in The Color of Magic by Terry Pratchett, there is my favorite character who's called Two Flower, and he's a tourist who just visits this kind of magical continent. Like he's visiting the Discworld, traveling around. And all of a sudden he was captured, and he sits somewhere in a cell. He's kind of locked up, and all of that. It's very dangerous. And he thinks about the dragon, and then the dragon appears. And then he has a very cool discussion with the dragon, like, how did you happen to be here? Well, you thought of me, and I thought of you, so here you are. Yes, so I am yours to command. The point is, these are dragons that appear the more you think of them. And then there's a funny line that says something of the sort that in this place, the veil between the thought and reality is somehow blurred. And something that we found, and that was a strong thesis we had as we were starting this to work on this project, was that thoughts correct memories. That thoughts themselves have actually an impact on memories, and yeah. So this is, let's say, this. It's
Wow.
more than just a cool,
Yeah.
fantasy reference. It's really
I
about how thought can shape what we remember, and then ultimately what happens.
Wow, I love that. That's one of my favorite stories for a naming of a product that I have ever heard. That's so cool and so thoughtful. Yeah.
But actually, it makes me come back to what you were asking before, the limits, right? We had the
Yeah.
memory problem
Yep.
and latent thinking. So latent thinking is the abstract thinking. Thinking's in
Okay.
something that, is freed of language. And all of a sudden a thought can be a concept. It can be something that multilingual people experience, I think, pretty often. They feel that, they can't really put like a finger on that word, like what the word is, but they know there is a concept there. When you put them together, you actually see that memory and time can feed the thought process. And I mean, hopefully, of course, like the path forwards for the entire field is to get to AGI. I mean, you call it however, like, but we want to build autonomous systems, and you kind of need to have this dimension of time and memory feeding your thought process, and thought process having, in fact, an interaction with what you remember, to build those reasoning frameworks, to build reasoning shortcuts, such as when you play chess with someone, I mean, I often ask them kind of, why did you make this move? Because I'm learning. And very often they kind of just, they can't really explain it. It's like, I just
Sure.
knew this one made sense.
Man, it's so fascinating. I have so many questions for you. So I'm gonna try to queue them up and get to them. And I'm also thinking about what the audience, I'm sure the audience, as they're listening to this, they have lots of questions, too. But so you started with the paper, October of 2025. You released your paper, and you said that the paper was well received. There were some other ones that happened around the same time that really challenged the idea of LLMs being the path to AI, the future of AI. That because of these limitations, the AI that we're building needs to transcend that. The product you're building is Dragon Hatchling, or BDH. Is the product released? How can people, or when will people be able to start experiencing, the difference for themselves of what this looks like compared to, what they've been used to using with the chatbots of today?
So to answer this question, I'll go back to the dogma of differentiation and to
Okay.
creating modes. And I think this is, if we're talking, maybe in the audience we have some startup community, what makes sense to build right now? What does make sense to build right now? So I think it's extremely important to have a very deep mode. And the more time we can spend on building the mode, the better it is for us in our case. So we are still focused on the architecture. What we showed to the world is the architecture, and we are training models based on it, making them shine in places where transformers somehow struggle. So notably, we're talking about memory and reasoning and costs. We will be releasing them, and you will be seeing the journey. We'll be releasing, benchmarks and the signs of smoke. This is also part of why the naming after dragons. This is a magical creature that has magical properties, even at small scales. Knowing that at our lab we already have stuff, working at 500 billion parameters. But as you work through the moding, you want to work the fastest, and you want to see signal at smaller scales. So we mostly work on the architecture and still work on the architecture. This is pretty locked, but let's say doing some stuff around it still to make the mode deeper. So the products will come. We have a great partnership with AWS. So the moment we press start, it's going to be available there. And we are lucky to have a number of design partners right now with whom we're kind of, mostly working around the use cases in long horizon reasoning.
Okay.
But
So that's where agents come
this is
in.
something that will come. This is something that will come, and I will not, commit to a date right now.
Sure.
But what's there is that along with the paper, we published a repo with let's say, the most vanilla version of the BDH architecture.
Okay.
It was fun, mostly for the purpose of allowing researchers to replicate the results of the paper, and many people actually started experimenting with it. That one is not yet the version that will take you all the way to solving, Sudoku at 97.4, things that we've done, a percent and all of that. But it's the one that shows the theory and shows the link between the transformer models, the transformer and the models of the brain. And this link we've shown formally in the paper. So we actually launched this paper to give this to give the science of AI to the AI community.
Okay.
So products are coming, don't worry, and actually pretty impressive. We'll be announcing kind of things as they come, as we kind of feel comfortable sharing. But there's stuff that many people play around with already, and there's also many materials about how you can think about basic mechanisms, or like main mechanisms of how AI works, like how attention works in BDH. There are talks by our CTO. So I would invite you to have a look at our YouTube channel for that. And yes, there is the GitHub repo and folks replicating the results, which is a lot of fun. We love seeing that.
A couple of the other things that come up with LLMs often, you mentioned one of them, but one, of course, is hallucinations. The other is safety, that you can, you can do prompt injection. You can do various ways to compromise, jailbreak, however you want to call it, the models themselves. And so is the work that you're doing and that you and your team are what you and your team are building, at Pathway, are you working on those problems as well? Or are those problems, will continue to be durable?
Well, they will continue to be durable to an extent that we as humans hallucinate quite a lot.
Sure. Fair.
But a lot of hallucinations come from the problem of context and generalization over time. So you kind of want to increase the window of focus for the model. Like, are we dealing just with the memento day, or does the person remember all the past and then can have an intelligent conversation with you, knowing your context and knowing everything else? So as we kind of hit this generalization over time, then number of hallucinations will just decrease dramatically. So of course, with enhanced reasoning and this notion of time, we will reduce hallucinations to something that will be probably more likely for a human, right? Safety, I think, is critical. We solve it from, let's say, for now, or we contribute to solving it, I would put it this way, through having understanding of how such a system works. Because right now, this is another limitation that we didn't mention. Right now, we train the models, they perform on benchmarks, we see the steam engine, showing steam, good. But we didn't really know why. So folks are building like the equivalents of MRI machines to scan the brain or the engine, to scan it, to try to see what happens there, and then explain, that was, the grandmother's cell, this is it, the Golden Bridge was here, and kind of pop up champagne every time we found something by scanning the brain and trying to sort kind of through what happened there. With a more theoretical approach, we actually see concepts emerge. And in BDH, this is what we show in the paper, you can literally locate the synapses that encode specific concepts that fire up when a concept like of a currency is mentioned. And since we have this micro to macro passage from small interactions between neurons to the global state and, to seeing a thought, the model doing something, we can predict that the same laws will hold at different scales of size and time. And this is something we can't really do for transformers right now. We can kind of, assert what they're doing on the given benchmark. We've seen them here, we know how they behave, but as we move outside of the tested conditions, it's difficult to say. And with it's like having some basic laws of how physics works versus not having them.
Sure.
So we have those laws, so we have a greater, I'd say, so maybe certainty about what will happen at different scales. I mean, we know the same interactions, like the local rules of neurons interacting, passing on information, reinforcing themselves. I mean, the equations of reasoning will hold no matter the scale. And this is actually, that's, I'd say, for now, our answer to the safety questions, in part why we embarked on this journey, because we believe that it is somehow difficult to launch systems that we fundamentally don't know how they work, and just put them out there, hoping for the best.
So that improves observability. There's this word observability that comes up a lot,
Somehow,
trying to understand.
Yeah, and interpretability, I'd say.
Interpretability. Okay.
This is one. This is what happened like after, but also as you design new experiments, as you kind of think about how your model will work at the new scale, what can happen. I mean, this helps you to predict things that you haven't tested yet.
Okay.
It's like scientists build something in space. I mean, they're not there in space to make the experiment right before building, but they can plan it very, very accurately, right?
They can model it. They can, anticipate all of the variables, and then they can build something based on those variables.
Exactly. So you can simulate stuff better.
Okay.
And this is something. So we believe that. Actually, we have a piece of content that we were writing about this. We believe systems based on BDH will have a greater chance of avoiding the paperclip factory problem. So of them going off rail, even set on a good goal, right? Them going off rail just because they kind of thought something was okay.
That's the explain the paperclip phenomenon.
The paperclip phenomenon is that, I mean, even if you have a model set on a positive or neutral goal, it may all of a sudden decide to use all the resources of the Earth to just turn it into a huge paperclip factory. Hence goal was maybe just to produce a paperclip. So
gotcha.
We would like to get to systems that at least we know, even if we put them to a goal that's reasonable, it won't do something crazy. It's a bit like when you're interviewing a candidate for a role at your organization. You know they graduated from, Harvard. You observed them for a couple of hours. Your team talked to them. They said that they liked them, right? And you expect that when you put them on the job, well, they will they may make some mistakes, but in general, they're predictable, right? They will behave like a human with this resume, kind of with this psychological profile, unless they have an unfortunate case of a mental illness. So for LLMs, we can't really know if they have a mental illness because we wouldn't even be able to define it. I mean, right now. And the thing is that with systems that we understand, we have a greater certainty that they will behave in a more predictable. Okay. And then setting them to a bad goal or prompt injection, attacks, and all of that. This is, let's say, not to be addressed exactly at this level, but.
But you also have said that, and you brought it up a little bit earlier too, that the way that you're building the models is also going to make them infinitely cheaper and use less compute. Maybe infinitely, I might be exaggerating, but
infinitely maybe, but I'd say that it is very impressive.
Okay.
Just how big of models we are able to train with how little compute. This is one, and also how extremely inexpensive they are to run. So first thing comes from the principles of BDH. So BDH got its inspiration from what biology got right, let's say.
Okay.
So we have local interactions between neurons. So not every neuron, not the entire brain fires up every time you have a question. You just fire up a couple of neurons who are connected. So you have sparsity, we have a number of things that actually we do observe in the brain. But we use those very simple kind of principles, apply them in BDH, and this leads to just general computational efficiency that we have, and the capacity to store a lot of a lot of memory to store it directly inside of the model. So this is fun, just a smart, efficient data structure. The second thing is that since we don't need to do chain of thought, because in our models, reasoning happens in this abstract space, we don't need to verbalize every step. It doesn't explode. It's extremely efficient. So the Sudoku result that I mentioned, that was like 97.4 pointers, was like state of the art when it happened, and just LLMs were at 15, I think, percent. I mean, this happens one shot without chain of thought immediately. It's just done. It's
wow.
This is a nice example, which is a nice illustration because everybody knows what Sudoku is. But in fact, these are like any constraint satisfaction problems, like planning your trips with your fuzzy constraints that, maybe your model after a while should know that you like your coffee at 8 and you like it with milk, and and maybe that latte place in Rome is closed on that day, and there are so many constraints that can come from context and that would make your planning easier. It's like, I don't know if you have an admin, but having an admin that's known you, again, it's a bit like the doctor who knows
Sure.
Yeah. So the costs, the difference in costs is dramatic. And the second thing is that training of the models is way less expensive. They don't need to ingest this much data. In fact, they get bored when they see something for too many times. This is something we already have in the BDH paper. We see neurons getting bored. Like when they hear the same thing for let's say another time, their activity just goes down. So we can observe it. We actually see what the neurons are doing, and we see they're getting bored. And then everything sits in memory, so we don't need to, since we have state. So point is, let's say context sits inside of the model, so we don't need to just, in the engineering sense, go outside of compute to fetch data elsewhere. So this reduces costs as well.
So you've just made it dramatically more efficient with the way that you've architected the way the model runs.
Yes, it's works like a brain on GPU.
Interesting, like a brain directly on the GPU. It makes sense in one sense too, because we know that the amount of power or energy that the human brain uses to process a question is so infinitesimal compared to what an LLM does.
Exactly.
Right? Yeah. Okay. Very good. Well, Zuzanna, I want to ask you, how did you end up on this journey? What is your background? How did you end up working in this sort of set of problems? And how does some of the things that, you learned along the way in your academic background and the projects you worked on before sort of lead you to this moment, where you're working on Pathway?
I was a researcher at the Institute of Complex Systems of Paris. And so complex systems is let's say, a funny discipline that merges many different disciplines in one, mostly looking at how interaction between small particles or small fundamental elements, let's say, give rise to global phenomena. And this can be anything. These can be atoms, this can be water, this can be people interacting on a social network. Point is, we have some units, there is something that happens in between them. And as we have many in-betweens, something happens, like information spreads and you have a rumor that starts, forming. This may change the result of elections, for example, right? So this is some of the topics that my colleagues were studying. It actually draws a lot from statistical physics. So actually most of the people have background, in complex systems have background in physics. I was working on the intersection of theoretical computer science, economics, and physics. I actually got into this through game theory, because my dad loved the movie The Beautiful Mind.
Yeah.
And I took a class in game theory once at Stockholm School of Economics. I fell in love with it, so I decided I needed to do it for the rest of my life somehow. And then I discovered graphs actually around the same time, working at Spot, which was the first and largest community for competitive programmers. And it was created by people who worked on data structures and graphs. So I learned a lot about graphs and networks back then. And then I started to do game theory on graphs, and then having those graphs evolve, so you kind of don't know what's happening anymore because everything keeps on changes, and the only constant in life is change.
Yeah.
And this is how I got to developing a very, very deep sense and intuition about how complex things that happen can be in fact reduced to small number of rules. And maybe fields or attractors that you place somewhere that can shift the behavior, but you can somehow not maybe solve the complexity or remove it, but you can put it in some sort of frame, so you can harness it somehow. And funnily enough, I mean, we were working already somehow on this project, but I think this is a story I told when we met. I was sitting with a friend who was a neuroscientist, like a wonderful man. So we're sitting there at a cafe in Paris. Imagine, beautiful Paris around kind of Saint-Michel, Notre Dame. We're there talking about different types of coffee, and then like porcelain, fine porcelain, and all of that. So we're kind of chatting. It's beautiful. And then all of a sudden, he tells me that there was an experiment when somebody swapped the auditory with the visual nerve and the mouse. And you know what? Like the mouse turned out just fine. And I sit there, I look at him and I say, yes, because function shapes the network. And then he looked at me and he said, yes, exactly. And then I stood up and I just left him. I went to our office, and I remember that was the moment, we were kind of already working on it, but it was a moment of a very, very clear conviction. So if we see it at the level of nerves, it wasn't the moment of the decision, but I remember this very deep conviction that yes, of course, function shapes network. And then we worked through, we had to go through the journey. But I made a number of bets with my colleagues, with Adrian and Diane, and I won each and every one of them. So funny enough, I did my PhD thesis. And it was published by Academy of Sciences on forecasting of maritime trade. I did forecasting of maritime trade because I had a great database. So I could actually see, having 30 years of daily movements of ships around the globe, this is a beautiful data set of a complex system coming alive. And what we found is that if you look very closely at attention in BDH, and how neurons pass on information, it actually behaves a bit like a transportation system. That's the easiest intuition you could have.
Okay.
The routing of information and the routes that are being used more just become wider.
Interesting. Okay.
So this is like, funny enough, you do find same dynamics. Just forget the system, the actual system that you apply it to, but you tend to find the same dynamics. And funnily enough, we found that the functions we see in models are somehow similar to the transportation ones. It's not a direct, equivalence, but a nice way to explain it.
Very cool. Wow. Okay. All right. I want to ask you, as we wrap it up, I want to ask you the same questions that I ask everybody right now, because there's these same two questions that I hear all the time in the AI industry. And one is, the promise of AI was that it was going to automate away a lot of the hard things, the sort of the grunt work and those kinds of things for us, and make us more efficient and essentially give us more time. But the reality is most of the people right now that I see, they feel like their time is stretched even more, thin, maybe because of they have more capabilities at their fingertips or whatever the case may be. They see sort of these new opportunities and they can do, more things. So because of that, leaders, all of the leaders I know right now are very conscious of like, how do they get maximum leverage for their time? How do they optimize, their time for maximum leverage? So I'd love to know, from you, what is your best tip? What are the thing that you've learned? What is it that you do to maximize your time right now, to get maximum leverage for your time, and that you might recommend to others? What's your best tip?
I'd say in general, in management and running the company, everything changed so much, right? So the only constant in life is change. It's never been as real as right now.
Yeah.
What I do, and I do it every day, and I do it before every meeting and every discussion, is that us as a team, we analyze the critical path. And it may change because you discover new blockers, right? But be ruthless about the critical path. And then have a culture about critical path that, okay, things have to be dropped. There's no, this is my area, this is yours. No, critical path is a religion. So this is one. Second is that we stopped coding. It's very weird to have a team full of competitive programmers, people who were, for example, coding in Rust when Rust went out, like, that level.
Yeah.
Who don't code anymore. It's very weird. It is a transition. It was a huge boost in productivity. And it wasn't possible, it was, let's say, enabled in winter. But we stopped coding, and it means you have to actually somehow make the team change their habits of working. And since all of a sudden you're producing 5 design docs a day instead of 1 design doc for a month, or like whatever, the quality of design docs doesn't need to be this good. Hopefully it's really good, but it doesn't need to be this good because the cost of producing code is not that huge. But then also your quality expectations from the code shouldn't be the same as what you've been expecting before. So there's a lot of change management, but going through it, a boost is just incredible. I hear people, pretty much being frightened by their token budgets exploding, right? And people just throwing into AI everything. I think, indeed, first of all, we'll just make it cheaper. Don't worry.
Yeah. You're working on that.
That's going to be fine. That's a solved problem. But second is, it requires different working habits. Actually, you may work for, like, instead of whatever people might have been doing in enterprise. And I'm a startup founder. I work all the time, so I'm not a regular person.
It's not normal.
I guess
know.
I'm just representative. But you can't really work from 9 to 5. But perhaps our workday should be rethought. Maybe we should be working such a way that we have one session, deep code, that kind of conceptual session. We launch the tasks for our Codex or Claude. Then we come back, right? When we go, we enjoy time with friends, or we do yoga, whatever. Then we come back. So we have breaks, but we work until the evening. And then, of course, because also what you want to optimize is the use of your hardware.
Sure.
And this is something that we've seen as a very huge change in the team. And yes, we collapsed, roadmaps from that. I guess a year ago would have taken way more people, and maybe a year, 2 weeks.
Very good. Okay, the last question that I ask everybody is on AI tools. And you've mentioned a couple, but maybe if there's any other ones as well, of what are the AI tools that right now you are using that maybe people aren't aware of, or using them a way that they might not be aware of, that are making a huge difference for you, huge impact, for you, and that you would recommend, people consider?
I mean, get the strongest subscription to the strongest coding models out there. But the color that I can add to it is that we see that folks who are doing the most cutting edge at Pathway, who are competitive programmers, they prefer Codex. And also we kind of know how it was trained, so it's not weird. Actually, the research team at OpenAI comes from competitive programming backgrounds. So competitive programmers go with Codex. folks who write, let's say, more traceable regular code, they definitely prefer Claude. So this is one fun thing to know.
Okay.
But definitely worth it. Getting the best subscriptions. It's incredible. Fun thing that I just noticed, I'm still experimenting with. You guys may know of Inflection AI. I'll do it again.
Okay.
So another cool thing that I'm just experimenting with is a model from Inflection AI, which is good at emotional intelligence. So when I write, pieces of content, I wanted to have a better voice and sound a bit more like me. And I'm starting to have pretty interesting results with that one. I haven't done tests like could I really find a good prompt for GPT or Claude to get me to the same level of emotional color. But so far I'm kind of pretty happy. So this is at least I think fun avenue for experimentation.
Very good. Those are great tips. Well, Zuzanna, thank you so much for being on the podcast. It's been such a great conversation. I knew it would be, from the time we met in San Francisco, and I learned a little bit about what you were doing. But this has been amazing to really unpack, all of these things. And best of luck in hatching your Dragon Hatchling later this year or whenever the occasion comes.
Now, it's big and flat.
It's getting big. It's good. It's good. No, very exciting. Thank you so much for being here.
Thank you. It was lovely and great seeing you.